All right, so the topic of big data is a topic where we have a lot of information, a lot of data, mostly written out in files on a system, usually organized in a database, but not necessarily. It could be videos, pictures, and the pictures could have names on them. And we need to search the data very quickly to get the results we want from our databases. So a traditional database won't return the information quick enough because there's too much data in it. So if we scatter it and use techniques we'll talk about is RAD systems, clusters, and then Hadoop and Hive. Okay, so the idea of big data, which is kind of an official computer science term, has come up probably in the last 10 years with a lot of applications like Twitter and Facebook. So this is just a cartoon where two ladies sitting at a restaurant and the waiter comes over and says, "Is everything okay? You're not taking a picture of your food," right? So a lot of people now go out to eat and their food comes and they take a picture and then they put it on Facebook and they put it on Instagram and then everyone comments on dinner and then they start putting pictures of their food. So all of these pictures have to be entered into a system, and then whoever your friends are gets a copy of the pictures, and there's lots of data that has to be calculated and searched through very, very quickly. So the concept of big data, it's not just so much the size of the data, but also something like the velocity of data, volume of data, and variety of data. So for an example of velocity of data, could be using EasyPass. When driving out on the highway, many years ago we used to have toll booths where you pull into the toll booth and an arm comes down and you pay a human being money, and then when they realize you pay, they hit a button and the arm goes up and you can drive, and then the next car comes down. So now you can get an EasyPass tag, put it on your windshield, and you open up an account, and in that account you can connect it to a credit card or send them a check, and they keep your balance. So when you go driving through the toll, depending on what you're driving, you could be driving a car or a truck, and different cars and different sized trucks have different tolls that you pay. So they would now have no person there, but a sensor would read the type of car you're in, how many axles, how many wheels do you have on your truck or car. And they would read your tag, you would log into a database, they would read your current balance, they would calculate against what you have currently owe for this trip through the toll booth, check your balance, see if you have enough money in your balance to cover this bill, and if so, they will say, you're paid, and you drive through. And if your balance is low, maybe they'll give you a warning, hey, your balance is low, maybe you should send in another check. If you don't have enough money in your account, they'll say, you didn't pay. I don't know, take a picture of your license plate and then report that you didn't pay. But they have to do all of that as you're driving through. There's not a lot of time to log in, check your balance, and then run some software that says your balance is this much and you owe this much, and then send out the warning message. You have to do this very, very quickly. So it can't just be a database table with every single person in the country who has an EasyPass and look through that. You have to find out techniques for accessing this data much quicker. So it's not only the amount of data, but sometimes even the speed at which you have to get the data. Volume of data is obviously very important. So for example, if Facebook has over 1 billion users and you want to check for login, we don't want to have you log in and then you give your password and your email and they check that against 1 billion emails until they finally find you in a database. That could take too long for you to log in, and then you wouldn't want to use the product. Twitter, for example, has 400 million tweets per day. Where do the tweets go? Well, it depends on who's subscribing to your tweet. They get a copy. And then also the different types of data. You have text messages, pictures, movies, etc. So another application, again, is Facebook in that case. Okay. So just an example of we're just going to do some very quick math just to get a point across. Suppose we had a traditional hard drive, and a traditional hard drive these days has a speed of about 100 megabytes per second. A solid state one, a better one, has maybe 500 megabytes per second, can be read. So suppose, for example, Facebook has 1 billion users. It actually has more than that now. But suppose Facebook has 1 billion users, and a table contains the user IDs, which is your email address, and password. Let's say they had a table that had only those 2 columns in it. And so let's say your user ID, they allow, let's say, up to 40 characters for a user ID, and then they encrypt your password, so they encrypt it, let's say, into a 25-character encrypted value. So 40 characters and 25 characters is 65 bytes per row in the table. Okay. So if you have 1 billion users and the table has 65 bytes per user, you're going to need 65 gig to hold this table. So if you wanted to read the 65 gig on a disk drive, a solid state, a very high speed drive that could read 500 meg per second, it would take you 130 seconds to read through this disk drive, which would be, if you're searching for somebody sequentially, not using an index, just sequentially, it could take you over 2 minutes to find a person or find out that this account doesn't exist. And if you were to log into Facebook and it took you a little over 2 minutes to log in, after a while you stop using it, right? So we can't do something like this. And even if we started using indexes, which builds like a binary tree, it would still take too long to do this. We have to find a faster way to search for data when the data gets to be so big. Okay, so suppose you had a disk drive that contained your database, and your database had blocks 1 through 8. So one copy of your database had blocks 1 through 8. That's your entire database. And we're going to be doing searches on the database sequentially. That could take, a linear search, we'd have to go through each of the 8 blocks. But suppose we decided we have a lot of disk space, so we're going to make 2 copies of every block and put them together, bundle them together, maybe the odd blocks, 1, 3, 5, and 7, and make 2 copies of them. And then we'll take the even number blocks and make 2 copies of that. Well, what would be the advantage of making 2 copies? Well, we can search, one application could be searching block 1, and another one could be simultaneously searching for something different in block 1. And then what would be the point of, so the redundancy would be so we could do multiple searches at the same time. And the fact that they would be independent of each other is that we could do the searching simultaneously. So we could have 4 disk drives and have the odds on one side, the evens on the other side, and have multiple copies of it for quicker searching. So now what we're doing is we're searching for something. We're saying we'll search this set and this set simultaneously, and then take the 2 answers and build them together and somehow hash out what the results are. Okay, so this is RAID, which is the redundant array independent disk format. Okay, so this would help us get answers quicker. So just some terminology. A node on a big data searching apparatus. A node is a computer with a CPU, processor, and some local disk drives. What we're going to call a rack is a collection of nodes connected together with very high bandwidth, so they can gather data and send the data that they find important to each other very quickly. And then a cluster is a collection of racks, and a rack is a collection of nodes. So, for example, a Microsoft cluster server, 2-node Microsoft cluster server, is basically we had some people in an office sitting at a computer and maybe a printer, and they need to go access data very, very quickly, large amounts of data very, very quickly. So rather than have the data on each of their machines, we have them put together in a cluster. So we have 2 cluster servers, and the 2 cluster servers are connected to RAID disk. disk sets. So we could have the odd disk here and the even disk here, and then both of these cluster servers could be reading from both of those together, doing searches and simultaneously looking for data to get a report that one of these users could use results very quickly. Okay. So, there's a framework. So a framework isn't a product. It's not a product you go down to Staples and you buy and you install it on a machine. It's basically a set of concepts that if you have enough equipment, you follow this procedure when going to search for something. So Apache, which puts out a lot of freeware, currently maintains Hadoop, which is an open source framework used to distribute storage and processing big data sets, using a concept called a MapReduce. I'll just go over that kind of briefly. So it's a framework of tools that consists of computer clusters built on commodity hardware. And the name doesn't actually have any meaning at all. There's some stuffed animal they used to sell, which was called Hadoop, and that's who it was named after. So the logo is this yellow elephant. So when you see that, you go to download this for free, you'll see that logo. Okay, so now for today's talk, I'm not saying that we have as a prerequisite, the understanding of how files are written on a hard drive, but just you may know from your operating systems class, you may know that files can be written on a hard drive many different ways. They could be written contiguously, meaning all the data is in a row. They could be written as linked files, where pieces of the file are scattered throughout the disk drive, and then links tell you the address of where the next piece is. Another popular style, which is used in Linux, is an indexed file, where the first piece of the file is a series of pointers to where all the pieces of the file are, and then you look in the index, you know where all the pieces are, and then you go gather up all the pieces. So, so what is the advantage of, why do we have so many different ways of writing files on disk drives? Well, different operating systems use different styles, and they're all trade-offs between how much time does it take to write the data versus how much time does it take to read the data. So if you're going to be writing and if you're going to be writing a lot, you use one style. If you're going to be reading a lot, you use another style. It's a mix of the two. It may not matter. But since Hadoop is going to be a system that collects data from many different operating systems, we could have data on a Windows server, we could have data on a Linux server, we could have videos on YouTube, and we're trying to gather all the data that has something in common with each other. Someone did a search on something, we're trying to gather up all the data from all these different file systems. Hadoop has its own file system, where the files are written in such a way that it's easy to find stuff in the file. It may take a while to write it, but it's easy to find stuff. So so Hadoop has its own file system, which kind of sits on top of all the other file systems. So we might take a file on a Microsoft Word, a sequential file, a file that is contiguous on the disk drive, and we might make a Hadoop copy of it where it's highly indexed, so we can find stuff on the file. So, so the Hadoop file system kind of sits on top of all the other file systems that are put together. So now, if we have some big piece of data, we're going to go search for something, and let's say there's pictures, files, videos, and you're searching for something. What's something you might search for that has different formats of what you're looking for? Maybe you're searching for a famous person. Anything? Have you guys done any searches today?
Like pages.
A what?
Like pages, Facebook pages.
Okay. So let's say you did a.
That's not really strange, though.
What's that?
But that's not really strange. It's pretty common.
Yeah, but let's just say maybe a new movie's coming out, and you do a search on the movie. So that could be. There's many actors in the movie, so you might want to get data about all the different actors in the movie. You might want to see a film clip of the movie. You might want to see some pictures from the movie. So there's all different stuff on all different systems that you want to gather up and eventually present to the person, oh, here's stuff about that particular movie you asked for. So we go out to the random world of data, have it all kind of put into indexes, then start gathering it kind of into stages where it makes sense for what it is you're searching for, and eventually gets to the useful data which we'll present to you. So, here's an example. It's kind of a silly example, but suppose we had 4 different statements. Right, so this is the play on the Peter Piper, pick the peck of pickled peppers. You know, so the thing that's hard to say if you say it very fast. So here's 4 different sentences that kind of have those same words repeating in them. So suppose we wanted to ask a question like, now, so, all right, so think about this. This is an example that came from the Hadoop web pages, the Apache web pages that give me an example of how this works. So suppose you wanted to know, suppose that these are 4 different tweets made by 4 different people. And you want to know, what is everybody talking about these days? What's trending? What's popular? What is everyone chatting about? What words show up a lot? So you would take this tweet, and you want to count up how many times a word showed up. Then take this tweet and count how many times does that word show up. And the idea is to eventually have all of these tweets say, what are all the words they have in common, and how many times do those words show up, so I can figure out what, what everybody's chatting about these days. So you read this sentence, and you do a computation. How many times does each word show up? And they all showed up 1 time. This is a slightly different sentence. How many times did these words show up? You count those. And then the same for here and here. Now you take these 2 sets of words. So here's the sentence. This is what the tweet was. And then this is an analysis of the tweet. How many times each word showed up. So this gets put into a table. So this was uncensored. This could be, a sequential, this could be indexed or something like that. Now we're putting it into a Hadoop file system where it says this word has showed up this many times. We have a table. Now we take this table and combine them together and get a count. How many times did Peter show up? How many times did Peter show up? It showed up 1 time here and 1 time here, so therefore it showed up 2 times. So this table represents from these 2 nodes. So this could be 2 different nodes on our cluster. Right? It could be hundreds of millions of tweets, hundreds of millions and so on, and we're trying to gather up a count at the end. So now this whole count, this is how many times the word showed up. And then from this sentence and from this sentence, here's a tally of those 2. Now we take these 2 and and make one small one. So we're doing this in stages so we could do it in parallel. If we did it sequentially, we'd have to go through every sentence and figure out what words are important, and our table would get bigger and bigger. And the whole thing would have to be done sequentially. So if we do this in rows, in waves, we can get to this table quicker. And the reason why this would be important data is this is symbolic, of course, but this is what words are showing up at a higher rate. And then apparently this is what's important. So if you're selling some products and everyone's chatting about some product, maybe you want to know that's what people are looking to buy now. So what this example is, it's supposed to think of it like, hundreds of millions of tweets, and you're taking all the words in the tweets and you're trying to very, very quickly say, what are people mostly talking about? And that data, this data, might be very valuable to know what people are talking about. So maybe, again, selling products or during an election, what issues are people chatting about, what's important to people, you could get that data from social media and then forming a table like this. Okay. And then there's a product called Hive, which once the data is all gathered up together, Hive is also, an Apache framework. It's a data warehousing software project built on top of Hadoop, providing data summaries, queries, and analysis. So you can do queries in an SQL-like, I call it a Hive QL, HQL. But it's an SQL-like interface to the data that is all stored using the Hadoop file system. And you could do queries against the database for it. So some of the features of Hive are it stores schema into a database and processes the database using the higher level Hadoop file system. And it is designed for OLAP, online analytics processing. Provides an SQL type language for querying the database, and it's fast, scalable, and extendable. It was originally created, Hive was originally created by Facebook, but then Apache took it over from them. So the idea is kind of, so what online analytical processing is, would be, an example could be if, suppose for example you had data, you had a company, and you had data for your sales from last year. The sales sales for every week or every day over the last year and the year before. And you notice that in the first quarter of this year, your sales are lower than the first quarter of last year. So what would you do? You want to know, maybe, did we have a bad week? Was there some hurricane or something? What was the reason for it? So you might query your database. Give me all the sales from the first quarter of this year, which is going to be a big query. Then take that result and do a query against the first quarter of last year. And then you look at the two results and you go, this year is worse than last year. Now what do? You say maybe it was from January or February or March. You don't know which month may have been the problem. So now you might do a query against January of this year, compared to January of last year, and you find those two seem to be similar. So the problem wasn't in January, so what else would you, what are other things you might conclude? What, I don't know, does that make sense, that you're doing a big query against a database from last year and this year. These queries are going to take time. And then you see the results, and that makes you think of the next query. What's your next query? Let me try February against February. Now, if it turns out that February of this year was much lower than February of last year, what now would be your next query? So basically what I'm trying to describe is online analytics. So you're analyzing data, and a lot of times you're doing a query against a large amount of data, and when the results come in, that lets you now decide what your next query is. And you could be doing this, all day long. So it's very important these queries are done quickly. So you might say, if my problem was in February, let me try each of the 4 different weeks in February and see if it was the first week, the second week, the third. And if it turns out it's the first and the second week with a problem, then you can say, let's see what happened during those weeks that our sales went up, so it doesn't happen again next year. So if you have all this data, and you know that people at your company are going to be going and doing queries based on quarters, months, weeks, daily queries. And these queries take time, because you have to do select star from transactions where the sales date was between February 1st and February 15th. And now you have to run through the whole data, your whole tables, years and years of data looking for those matches. So what are some things we could do? If we know we're going to be doing queries like this a lot, what are some things we could do to make the queries go quicker? Well, what we can do is we can take our data and say, well, I know people are going to be looking at by month, by weeks, maybe by groups of 2 weeks. We could run a query, maybe at 3 o'clock in the morning, run a query that tells us all the totals for every month from last year. And then, if somebody wants to know what happened in February and March, well, we already know what happened in February because we calculated that. We saved the results. We know what happened in March, we calculated that. Now we can just add those 2 results together if they want February and March. If they want, if we did for each week, we could do the first week of February, the second week of February, and if for some reason someone wants the first 2 weeks of February. We just take the first week and the second week, add it together, and that's the results. So we don't have to go through the whole database. We can kind of anticipate what types of queries they're going to do. Very large queries. We can do them in advance. Save that data, kind of like in this, do a query on here, save it in a table. Do a query on here, save it in a table. If later on somebody wants these two tables combined, we don't have to query the whole database. We just take this table and this table and sum them up and then give them that. So that's kind of at a high level. That is what online analytical processing is. It's where you have a massive amount of data and you're going to log into a system online, so you kind of stay logged in, and you ask questions to the system. And then when you get your answer back, you know the next question you're going to answer, and you query again. And you keep going over the same amount of massive data over and over. So you're going to spend most of your time processing your queries. Get a result, throw in a new query, and wait. So if we could pre-process all the data so that your answers would come back quicker, that would help. So, and that's a lot of how, Facebook works, right? You log in, and then we go through a whole query of who all your friends are. Then we gather up all the information about your friends. And then, different people have common friends, so we'll look at how many people you have friends, and then you might be interested in this friend. So gathering up all that data would be nice if it was all pre-processed and we could just put it together, rather than doing a brand new search every time. Okay, so like I say, this is pretty much a high-level talk. We could later on go into the actual. If we want to spend more time on Hadoop, we could talk about their particular file system, which is where they go out and gather data from various different file systems, import them into their own file system, which only helps them just find stuff faster. So we're taking this data, we're copying it into here. We haven't really found anything. We just processed our data into files that Hadoop can find stuff fast. Then it goes and finds out what's important and then starts reducing it to whatever we're querying for. So this would, again, back in this example. This could be data that's in random non-Hadoop format. We transform it into Hadoop format, so we haven't really changed the size of the data, we just reformatted it. And then we start doing analytics on it, counting stuff up, and then eventually we're getting smaller and smaller too. What we want to do is know how many times each word showed up. That's what we're trying to do with this big amount of data in this case.
Empty string. The empty string is the string with no symbols.
Okay, so any questions on that?